The last type of reaction that we're going to look at are oxidation-reduction reactions. In order to discuss what actually occurs in oxidation-reduction reactions, we actually have to define first what reduction is and what oxidation is. Reduction is the gain of electrons, while oxidation is the loss of electrons. The way that I remember it is oil rig. Oil, oxidation is loss of electrons. Rig, reduction is gain of electrons. So if an element is oxidized, its charge, because it has lost electrons, is going to become positive. If an element is reduced or it gains electrons, its charge will be negative. And so what we do in order to keep track of the loss and the gain of electrons, which is what is occurring during oxidation-reduction reactions, is we apply oxidation numbers. We also call these oxidation states. So by assigning these oxidation numbers, we're able to keep track of what atom, what compound has oxidation occurring in it, while we're also able to keep track of what atom has reduction occurring. So let's go over some of the rules for assigning oxidation numbers. The first one is that elements, so atoms in their elemental form, have an oxidation number of 0. All right? The sum of the oxidation numbers of a compound, assuming that compound is neutrally charged, is going to also be 0. And finally, the sum of the oxidation numbers for a polyatomic ion must be equal to the charge of that polyatomic ion. Now, oxygen, the oxidation number of oxygen is normally -2. Now, keep in mind that instead of writing 2-, which is the charge of oxygen, in order to distinguish between the charge of ions and the oxidation number, we write it in reverse. So we write -2 instead of 2-. All right. Of course, there's an exception. When you have peroxide, which is O2 with a -2 charge, then the oxidation number will be -1. When hydrogen is bound to nonmetals, remember nonmetals have a negative charge, its oxidation number is going to be +1, while when it's bound to metals, it's actually not going to be hydrogen, it's going to be hydride. It's going to have a negative charge. Its oxidation number is going to be -1. Now, fluorine always has an oxidation number of -1, all right? But other halogens, while they normally have an oxidation number of -1, when they combine with oxygen, they have positive oxidation states. And you can figure out the oxidation number of those halogens by assuming that oxygen has a -2 oxidation number and therefore figuring out their oxidation state. And we'll get plenty of practice with that. Group 1 metals will always have a +1 oxidation number, while group 2 metals will always have a +2. And keep in mind that the positive charge generally comes first when you're writing a compound. All right, so let's actually practice with a compound. We have potassium permanganate here, KMnO4. And so what I like to do is I like to start with the atoms for whose oxidation states or oxidation numbers I already know. So oxygen I already know. Oxygen is -2. Now notice you have 4 oxygens. Therefore, the oxidation state of oxygen is -2, but keep in mind that it's contributing a total of -8 because there are 4 of them. Potassium is a group 1 metal, therefore it's always going to be +1. And so to figure out the oxidation state of manganese, I know that oxygen contributes -8 to the oxidation state, potassium contributes +1, therefore to make sure that that compound has a neutral or no overall oxidation state or an overall oxidation state of 0, manganese must have an oxidation state of +7. Single replacement reactions are reactions in which we will see this oxidation reduction occurring. The general format for a single replacement reaction is you have A, which is an atom, and it's reacting with a compound with BX. And so what A is going to do, if you notice, A kicks B out, it replaces it to form AX plus B. And what you'll notice is that you have oxidation and reduction occurring. Keep in mind that in order to have a redox or an oxidation reduction reaction, one atom must be reduced while the other one is oxidized. You can't have reduction without oxidation. So if you look at this example right here, I changed manganese to magnesium just for simplicity's sake. If I have solid magnesium and it's placed in a solution with copper 2 sulfate, so it'd be CuSO4 since the two charges cancel. This is going to be a single replacement reaction. Magnesium is going to replace copper. Magnesium has a +2 charge, sulfate has a -2 charge. And then the other product is going to be copper. Now, let's write the complete ionic equation for this. So it's going to be magnesium still. Copper sulfate is soluble, so it's going to be Cu2 plus and SO4 2 minus. And magnesium sulfate is also soluble. And then the other product is going to be copper. So when I write my net ionic equation, what's going to be left is magnesium plus copper, and that's going to produce magnesium ions and copper atom. So if we now apply the concepts of oxidation and reduction, magnesium, and going from magnesium with no charge to a 2+ charge, it lost electrons, which means it was oxidized. Copper, going from a +2 charge to having a neutral charge, gained electrons, which means it was reduced. The last concept that we need to go over with single replacement reactions is the activity series. Now, the activity series helps us in order to anticipate which metals are going to be oxidized, because it is a list which, as you move up the table, indicates the ease at which metals are oxidized. So the top metal, lithium, is the easiest to oxidize, while gold is the hardest to oxidize. The general rule is that a metal is only going to be oxidized if it is higher on the table than the metal in the salt that it is trying to replace. So for example, if lithium is trying to replace sodium in, let's say, sodium chloride, it can, because it is easier for it to be oxidized than sodium, and therefore it can replace sodium. If instead you were trying to have nickel replacing aluminum, it couldn't, because it's lower on the activity series.